Hello everybody. In this video PowerPoint presentation, I will be helping you with an application of Cauchy residue theorem in contour integration. The contents of this presentation will have Cauchy residue theorem and introduction, the procedure for evaluating residues, definition of a type 1 contour integral, definition of a type 2 contour integral, problem based on type 1 integral and problems based on type 2 integral. Cauchy residue theorem statement. If f of z is analytic on and inside a simple closed curve C, except at a finite number of singularities inside C, say a1, a2, a3 up to an, and if r1, r2, r3 up to rn are the respective residues at these singularities, then integral over C f of z dz equals 2 pi I into r1 plus r2 plus r3 plus so on up to rn. Let us now look at the salient features of this Cauchy residue theorem. Number one, the curve that we consider should be a simple closed curve. Number two, the function must be analytic. There can be a few points where the function is not analytic, and such points we know are called singularities. Some of the singularities may lie inside the curve, some of the singularities may lie outside the curve. The number of singularities that are inside the curve have to be finite. That is, the number n, a1, a2, a3 up to an, that n has to be a finite number. For every singularity, the residue can be calculated, and that is represented by r1, r2, r3, so on up to rn. Then the Cauchy residue theorem states that the contour integral over C f of z dz that you can find on the left hand side of the statement in slide 3, now that is equal to 2 pi I into sum of all the residues. Now what we have to understand here is that the residues have to be calculated only for those singularities that are inside the curve. That is what the Cauchy residue theorem says. The formula for evaluation of residues, we have three formulas. If the pole is a pole of order 1, that is if it's a simple pole, then we use formula number 1. The residue is given by limit z tends to a, z minus a into f of z. If it is a pole of order m, where m is a number other than 1, maybe 2, 3, 4, 5, any number, then in such a case we use formula 2, and that is the residue equals 1 by m minus 1 factorial limit z tends to a of d power m minus 1 by dz power m minus 1 of z minus a power m into f of z. Please observe that the value of m must be a positive integer. So for any number other than 1, we will be using formula 2. If it is a pole of order 1, we will be using formula 1. In some special cases, we will be using formula 3 for evaluation of a residue. The pole must be of order 1 and the function must be in the form of a ratio or fraction, that is of the form p of z by q of z, where p of z and q of z are algebraic functions of z. Then in such cases we will be using formula 3 for evaluating residues. Remember, when it is a pole of order 1, we use formula 1. If it's a pole of order other than 1, 2, 3 or so, we use formula 2. Formula 3 is used in the case where the pole is of order 1 and the function is in the form of a fraction where the numerator and denominator are algebraic functions. Let us see what is a type 1 contour integral. The type 1 contour integral is of the form integral minus infinity to infinity p of x by q of x dx, where p of x and q of x are algebraic functions or polynomials of x. Such an integral is called as a type 1 integral. Observe the limits to be from minus infinity to plus infinity, and the two functions, the numerator and the denominator, have to be polynomials in x. Now this type 1 integral will have a finite value, that is it will be convergent if two conditions are satisfied. The first condition is that the denominator function, that is q of x, must be at least 2 degree more than the numerator's degree, that is of p of x. As an example, if q of x were to be a 5th degree polynomial, then p of x must be of degree 3 or less. Another example, if q of x is of degree say 4, then p of x must be of degree 2 or less, which means that the degree of the denominator polynomial q of x must at least be 2 more than the degree of the numerator polynomial p of x. That is condition number 1. The second condition is a very interesting condition. The roots of the polynomial q of x, that is the denominator, should not be real. q of x should not become 0 for any real number. That is the second condition. The values at which a polynomial becomes 0 are called as the roots of the polynomial, which means that the second condition says that the roots of the polynomial q of x should not be real numbers. Under the condition of q of x having degree 2 more than p of x and q of x not having a real root, the integral converges or it has a finite value. Let us look at the evaluation procedure for a contour integral of type 1. The contour is defined in this fashion. We consider the upper semicircle S colon mod z equal to R and the real axis from minus R to plus R. R is some positive number. Now mod z equal to R, we know in complex analysis, represents the boundary of a circle with origin as center and R as radius. We don't consider the complete circle, we only consider the upper semicircle, and that too it is taken in the anti-clockwise direction as shown in the figure in slide number 7. And apart from the upper semicircle, we also take minus r to plus r on the real axis. That is how the contour becomes a closed contour. If we consider only the upper semicircle S without minus r to r, it will be an open contour. But we consider S along with minus r to r, that's how it becomes a closed contour. Now this contour is to be used not just for problems of type 1 but also for problems of type 2, which I will be defining subsequently. Now what we do for evaluation of a type 1 integral is we consider over this contour that I defined in the previous slide, p of z by q of z dz. We convert or we replace x in the original problem with z and we consider the contour integral over c p of z by q of z dz, which can be evaluated using the Cauchy residue theorem. Once we have found the value of this contour integral, we may use equation star for finding the answer to the original question. Look at equation star. What is the contour C here made of? It has two parts. It is made of the upper semicircle S and the real axis from minus R to R, which means integration over the contour can be broken into two separate integrals, the ones that you are finding on the right hand side of equation star. That is the integration from minus r to plus r on the real axis, followed by the integration over the upper semicircle, that is S. That is why we get equation star. Now you may wonder why x is used in the first integral and z is used in the other two integrals. For the simple reason that z is equal to x plus iy. When we take integration from minus r to plus r, we see that that we are moving in the real axis. The equation of the real axis is y is equal to 0. So z is equal to x plus iy automatically becomes z is equal to x plus I into 0. That is z is equal to x. That is why we replace the z with x in the first integral on the right hand side of equation star. Now the value of the second integral on the right becomes 0 as r tends to infinity by what is called as Cauchy's lemma. The Cauchy's lemma has been given to you in slide number 8 for your understanding. So the second integral on the right hand side of equation star, that is integral over the upper semicircle S, tends to 0 as r tends to infinity. Now this we represent in the next equation represented by double star. So observe that the second integral on the right hand side of equation star, that is over S, became 0. And when does it become 0? When r is made infinity. So by replacing r with infinity in the first integral on the right hand side of equation star and by eliminating integral over S, the upper semicircle, we get equation double star. Now this is the methodology that we use for evaluating type 1 integrals. Now I've just given a brief working rule of the type 1 contour integral in slide number 10. Anyway, we will be doing problems for better understanding. Now let us see what is a type 2 contour integral. In type 1, please recall that the integral was integral minus infinity to infinity p of x by q of x dx. Here in type 2, other than p of x by q of x in the integrand, we will also have a sine of mx or a cos of mx. The presence of sine of mx or cos of mx in the integrand makes the problem a type 2 integral. Here again, p of x and q of x need to be polynomials. Now this type 2 integral will converge or will have a finite value if three conditions are satisfied. The first condition is m must be a positive number. Now m is the coefficient of x as defined in the angle of sine or cos in the integrand. So that m has to be a positive number. It should be greater than 0. That is condition number 1. Condition number 2, the degree of the denominator polynomial q of x must be greater than the degree of the numerator polynomial. There is no restriction that it must be at least 2 greater than the numerator's degree as in type 1. In type 2, the degree of the denominator q of x must be greater than the degree of the numerator polynomial p of x. As an example, if q of x, the denominator, has degree say 7, then p of x must be of degree 6 or less. If another example, if q of x is of degree say 5, then p of x must be of degree 4 or less. It must only be greater than the numerator's degree. That is what the second condition says. Third condition is the same as what we had seen in the previous type. The denominator should not have any real roots. The points x where q of x becomes 0 should not be real numbers. If these three conditions are satisfied, then a type 2 integral will have a finite value, that is, it will converge. Now the evaluation of a type 2 integral is similar to that of a type 1 integral with respect to the contour selection. We use the same contour as in type 1, that is, we consider a closed contour made of two parts, the upper semicircle S mod z equal to r and the real axis from minus r to plus r. So the same contour is used for type 1 as well as. The procedure of evaluation is slightly different. We consider integral over c p of z by q of z dz in the case of type 1. Here, the integrand consists of a sin mx or a cos mx. And therefore, what we do is the contour integral will consist in the integrand e power imz. If the original problem has a cos mx or a sin mx, we consider e power imz and write our equation star. Now the second integral on the right hand side of equation star becomes 0 as r tends to infinity because of the Jordan's lemma. We use Cauchy's lemma in making this upper semicircle integral 0 in the case of type 1. Here, in making the upper semicircle integral 0 in type 2, we use Jordan's lemma as r tends to infinity. The left hand side of equation star can be evaluated using Cauchy residue theorem. The right hand side, we put r as infinity so that the second integral becomes 0 because of Jordan's lemma, and star therefore reduces to double star that we are able to find in this particular slide. The original problem does not have an e power imx. So what we do is we rewrite e power imx as cos mx plus I sin mx, which I will be representing in the next slide. Yeah, you can observe that step number 4, we write e power imx as cos mx plus I sin mx because of the de Moivre's formula. And then we compare the real part if the original problem has cos mx in it, or we compare the imaginary part if the problem has sin mx in it. Now what comparison is done, real part or imaginary part, depends on what is present in the integrand in the problem that we have considered. With this we will move into a few problems. Yeah, please look at the first problem. What we are given is evaluate integral minus infinity to infinity dx divided by x square plus a square into x square plus b square using contour integration given a greater than b greater than 0. How do we recognize that the problem is a type 1 problem? Two things. Number one, the integration has limits from minus infinity to plus infinity. The second observation is it is of the form p of x by q of x. In this case, it is 1 divided by x square plus a square into x square plus b square. Dx represents the variable of integration. So for p of x, the numerator polynomial, we have 1, and for q of x, the denominator polynomial, we have x square plus a square into x square plus b square. That is how the problem becomes a problem of type 1. So in step number 1, we describe the contour. The contour is made of the upper semicircle S mod z equal to r and the real axis from minus r to plus r. The contour has been described. Now we will write equation star. I'm sure you are able to see that equation star is written on the left hand side by converting x to z in the original problem. Therefore, we have integral dz divided by z square plus a square into z square plus b square, and this is evaluated on the closed contour that we just defined. Now, what is a closed contour made of? Two parts, the upper semicircle S and the real axis from minus r to r, which means the integration over C can be broken into integration over minus r to plus r and integration over s, which is what has been represented in equation star. In step number 2, we will apply the Cauchy residue theorem. We consider the integral on the left hand side of equation star, that is a contour integral. Now what is our f of z here? 1 divided by z square plus a square into z square plus b square. We need to find the singularities of this function, which is obtained by equating the denominator to 0. That is how we get z square plus a square into z square plus b square equal to 0. But z square plus a square can be factorized using the formula given in the side, a square plus b square equal to a minus bi into a plus bi. With that, I will be able to write as z minus ai into z plus ai, z minus bi into z plus bi equal to 0. That is, we have written the factorized form of the polynomial. Now by equating each factor to 0, we get z is equal to ai minus ai, bi minus bi, which are the four singularities or poles for the given function f of z. Now how do we recognize the order of the pole? Please look at the factor for every pole. For the pole ai, the factor is z minus ai, which occurs with degree 1, and therefore it's a pole of order 1. If you look at minus ai, the factor is z plus ai, which also occurs with degree 1, therefore it is also a pole of order 1. In fact, all four poles here are of order 1. Now what are we interested in? The poles that are inside the curve and the poles that are outside the curve. Okay. Of the four poles ai minus ai, bi minus bi, we find that ai and bi are inside the curve and minus ai and minus bi are outside the curve. I will explain why it is so. What does the contour C consist of? The upper semicircle and the real axis from minus r to plus r. You know that the point ai, that is 0 comma a, is a point on the imaginary axis or the y axis. A being positive, 0 comma a lies on the positive y axis, whereas 0 comma minus a lies on the negative y axis. The contour does not contain the negative y axis. By virtue of this, minus ai is outside the curve. For a similar reason, bi is inside the curve and minus bi is outside the curve. So we find two poles that are inside and both of order 1. So we will be finding two residues, r1 and r2. Please recall that the Cauchy residue theorem requires us to calculate the residues only for the poles that are inside the simple closed curve C. So I'm going to be finding only two residues. For finding the first residue R1 at z equal to ai, I use formula number 1. Limit z tends to a, z minus a into f of z. Here it is ai. Therefore, we have limit z tends to ai, z minus ai into f of z. Rewrite the value of f of z, and that's 1 by z square plus a square into z square plus b square. Z square plus a square is written in the factorized form, z minus ai into z plus ai, and we keep as z square plus b square as it is. Now z minus ai is cancelled. On substituting z equal to ai, we get the result that is given there as r1. Please note that I square is equal to minus 1, and this residue 1 has been represented by equation number 1. Look at the evaluation of residue 2. The second residue is for the pole z equal to bi, which is also a pole of order 1, and therefore we use formula number 1 again. Limit z tends to bi, z minus bi into the function f of z. We rewrite the function's value 1 divided by z square plus a square into z square plus b square. Here z square plus b square is written in the factorized form, that is z minus bi into z plus bi, of which z minus bi gets cancelled, and by substituting z equal to bi, we get the result that is given in equation 2, that is the second residue. Now I will apply Cauchy residue theorem for evaluating this integral over C. What does the Cauchy residue theorem state? Integral over C f of z dz equal to 2 pi I into sum of residues. We have two residues, therefore we write r1 plus r2. r1 is replaced using equation number 1 and r2 is replaced using equation number 2. Now you can see that for the terms that are inside, the common values can be taken outside. Observe 2i and a square minus b square being a common denominator that has been taken outside. Observe that in this particular slide, we have taken that 2i into a square minus b square outside. So what remains inside is minus 1 by a plus 1 by b. By taking LCM, we get a minus b by ab. Observe that 2 and I are getting cancelled. A square minus b square can be factorized as a minus b into a plus b, where a minus b also gets cancelled, and that is how we get the value of the contour integral by Cauchy residue theorem, and that has been represented in equation number 3. Now let us apply the Cauchy's lemma. I'm going to be using equation 3 in the original equation star. The left hand side of equation star is integral over c dz divided by z square plus a square into z square plus b square, whose value is represented by equation 3. So we make a substitution to get equation number 4. Now the second integral on the right hand side of equation 4, that is integral over s, becomes 0 as r tends to infinity by Cauchy's lemma. So by using Cauchy's lemma, 4 can be further rewritten as pi divided by ab into a plus b equals minus infinity to plus infinity dx divided by x square plus a square into x square plus b square plus 0. We write the integral on the left hand side and the numerical value on the right hand side to get the final answer, which has been shown in a box. That completes the evaluation of the first problem under type 1. Let us look at a second example. Evaluate integral 0 to infinity x square divided by x square plus a square into x square plus b square dx using contour integration given a greater than b greater than 0. The first observation here is that the limits are 0 to infinity. A type 1 integral has limits from minus infinity to infinity, but here it is 0 to infinity. Yet we will be able to solve the problem for the simple reason that the function here x square divided by x square plus a square into x square plus b square is an even integral, and therefore we can apply properties of definite integral. Observe that the integrand is of the form p of x by q of x, p of x being x square, q of x being x square plus a square into x square plus b square. That is how the problem becomes a problem of type 1. Because it's a problem of type 1, in step number 1 we describe the contour in exactly the same manner as we have defined in the previous problem. That is, the contour is made of the upper semicircle S and the real axis from minus r to plus r. We write equation star, that is integral over the contour equals integral from minus r to r plus integral over the upper semicircle S. I'm sure you know the reason for that, because a contour is made of minus r to plus r, the real axis, and the upper semicircle S. That is how we write equation star. Now let us evaluate the left hand side of equation star using Cauchy residue theorem. The function in this particular case is z square divided by z square plus a square into z square plus b square. The singularities for this function are given by equating the denominator to 0. Z square plus a square into z square plus b square equal to 0, which is similar to the denominator in the previous problem, which means the poles are going to remain the same. The order of the pole, etc., will remain the same. We once again observe that there are two poles that are inside the curve, AI and BI. So for these two poles, we find the residues, and that is what has been shown in slide number 23. Observe that f of z is replaced with z square divided by z square plus a square into z square plus b square. Z square plus a square is factorized as z minus ai into z plus ai, and z square plus b square is kept as it is. Z minus ai gets cancelled, and then we substitute z equal to ai to get the required result shown in equation number 1. A similar application of formula 1 for evaluating the second residue for the pole z equal to bi. Same procedure, we find that the residue R2 here is represented by equation 2. The steps are very self-explanatory. I am sure you are able to follow them. We substitute R1 and R2 in the Cauchy residue theorem, which states integral over C f of z dz equals 2 pi I into sum of the residues, that is R1 plus R2. So we merely substitute R1 and R2. Observe here that a square minus b square, 2 and I in the denominator can be commonly taken outside, which is what I will be showing in the next slide. 2I will get cancelled. A square minus b square can be rewritten as a minus b into a plus b, which means a minus b also gets cancelled, and we get the final equation represented by 3. Now we apply the Cauchy's lemma. We will take 3 and put it on the left hand side of equation star, so that we get equation 4. Now by Cauchy's lemma, when r tends to infinity, the second integral on the right hand side tends to 0, and therefore 4 can be rewritten as pi divided by a plus b equals minus infinity to infinity x square divided by x square plus a square into x square plus b square dx plus 0, which I have rewritten as equation 5 by putting the integral on the left hand side and the value on the right hand side. Remember that the original problem has not minus infinity, infinity has limits, but 0 to infinity. So we further proceed in slide number 26 to solve the original problem. Now minus infinity to infinity, x square by x square plus a square into x square plus b square dx can be rewritten as 2 times 0 to infinity x square by x square plus a square into x square plus b square dx because of property of definite integral. If the function is known to be an even function, minus infinity to infinity of that function can be written as 2 times 0 to infinity of that function. That is the reason for which we are using that particular formula here. The integral on the left hand side is given by equation 5, that is pi divided by a plus b. Then we take 2 from the right side and put it onto the left hand side, and that's how you get the final answer. We write the integral on the left and the numerical value on the right, and the consolidated value has been given in the box in slide number 26, completing the problem. We take up another example for type 1. Here the integral is in minus infinity to infinity x square minus x plus 2 divided by x power 4 plus 10x square plus 9 dx using contour integration. It is obviously of type 1 because the limit is minus infinity infinity, and then we have the integrand in the form p of x by q of x. The contour is chosen exactly in the same manner as in the first two problems. We write equation star. Now by now I am sure you are able to understand how the equation star is being written. Then we evaluate the left hand side contour integral by Cauchy residue theorem. The function here is z square minus z plus 2 divided by z power 4 plus 10z square plus 9. So the singularities are achieved by equating the denominator to 0. That is z power 4 plus 10z square plus 9 equal to 0. Let us look at the factorization of this, which I have represented in the separate box on the right side of the slide. We put z square equal to t, so that we get t square plus 10t plus 9 equal to 0. Now we know that at square plus bt plus c equal to 0 has roots given by the formula t equal to minus b plus or minus root of b square minus 4ac divided by 2a. For a, b, c we have 1, 10 and 9. A is the coefficient of t square, which is 1 here. B is the coefficient of t, which is 10 here, and c is a constant term, that is 9. By substituting a, b, c's value, we get the roots to be minus 9 and minus 1. For the root minus 9, the factor is t plus 9. And for the root minus 1, the factor is t plus 1, which means t square plus 10t plus 9 equal to 0 can be written in the factorized form as t plus 9 into t plus 1 equal to 0. Now here we replace t with z square, so that we have z square plus 9 into z square plus 1 equal to 0. Now let us get back to the original problem. Z square plus 9 can be rewritten as z minus 3i into z plus 3i, and z square plus 1 can be rewritten as z minus I into z plus I. So we have that equal to 0. By equating each factor to 0, we get 3i minus 3i, I and minus I to be the poles. See that all the factors are of degree 1, which means all poles are poles of order 1. Among the 4 poles, the one that lies inside and the one that lies outside is what we have to find. Minus 3i is 0, minus 3. Minus I is 0, minus 1. So both of them lie inside, outside the curve. Whereas z equal to 3i, that is 0, 3, and z equal to I, that is 0, 1, are inside the curve. Okay, so for the poles that are inside, we evaluate the residues. The evaluation of residues has been shown subsequently. We use formula 1 because it's z equal to 3i is a pole of order 1. F of z is replaced with z square minus z plus 2 divided by z square plus 10z plus 9. Z power 4 plus 10z square plus 9, sorry, and then that is written in the factorized form, that is z square plus 9 into z square plus 1. Z square plus 9 is then factorized as z minus 3i into z plus 3i, and z square plus 1 is kept as it is. Z minus 3i will get cancelled, and by substituting z equal to 3i, we get the required result as represented in equation number 1. The second residue is also evaluated in the same manner. We again use formula 1 here. Here z minus I will get cancelled, and by substituting z equal to I, we get the result as shown in equation number 2. Then we consider the Cauchy residue theorem. Substitute R1 and R2 from equation 1 and equation 2. Observe 48i to be the common LCM for the denominator of the last step in slide number 30. By taking 48i, and then evaluating, algebraically reducing, arithmetically reducing it, we get 5 pi divided by 12, which is represented by equation 3. Now the application of Cauchy's lemma, we take equation 3 and substitute that in the place of the left hand side of equation star. We apply Cauchy's lemma that we take r tends to infinity, so that the integral on the second integral on the right hand side becomes 0, and therefore 4 can be rewritten as 5 pi by 12 equal to minus infinity to infinity x square minus x plus 2 divided by x power 4 plus 10x square plus 9 dx plus 0. We write the integral on the left hand side and the numerical value on the right hand side to get the final answer, completing the problem. A similar example has been done in problem number 4. You will surely be able to understand if you follow the steps. It is very self-explanatory. Slide number 30, 33, slide 34, slide 35, slide 36 will give you the slide number 31 to 36 will help you in solving problem 4. Problem 5 is also a similar problem, so I don't want to spend much time on this problem. The only difference is it has a limit 0 to infinity. You can apply the definite integral property to get the final answer. So slide numbers 37, 38, 39, 40, 41 and 42 are the slides that help you in solving the fifth problem. Now let us get into a slightly different problem in the sixth one. The question here is evaluate integral 0 to infinity dx divided by 1 plus x square the whole square using contour integration. The description of the contour is like how we have defined in the last 5 problems. We write equation star as always, and then we start evaluating the integral on the left hand side of star using Cauchy residue theorem. The function here is 1 divided by 1 plus z square the whole square equal to 0. F of z equal to 1 by 1 plus 1 by 1 plus z square the whole square. The singularities of this function are given by 1 plus z square the whole square equal to 0. 1 plus z square can be rewritten as z square plus 1, which can be factorized as z minus I into z plus I. Because we have the whole square, we have z minus I the whole square into z plus I the whole square equal to 0. By equating the factors to 0, we get z equal to I and z equal to minus I. Observe that for z equal to I, the factor is z minus I, which occurs with degree 2, and therefore it is a pole of order 2. Similarly, z equal to minus I, the factor is z plus I. This also occurs with degree 2, therefore this also is a pole of order 2. So for the first time, we are encountering a problem in which the pole is of order 2 and not of order 1. Among the two poles, z equal to I, that is 0, 1, and z equal to minus I, that is 0, minus 1, z equal to I lies inside the curve because it is on the positive real imaginary axis, and z equal to minus I lies outside the curve because it is on the negative imaginary axis. So for the pole that is inside, we find the residue. That is, we have to find only one residue here, and therefore I have represented it by R. But we don't use formula 1, we use formula 2 because it's a pole of order 2. Recall formula 2 of evaluation of residue. 1 by m minus 1 factorial, limit z tends to a, d power m minus 1 by dz power m minus 1 of z minus a to the power of m into f of z. In the place of m, we have 2 here, and that is why we have written the formula by replacing m equal to 2. Now f of z is 1 by 1 plus z square the whole square. 1 plus z square the whole square can be factorized as z minus I the whole square into z plus I the whole square, of which z minus I the whole square gets cancelled. Before substituting z equal to I, we need to differentiate 1 by z plus I the whole square, which is governed by differentiation of 1 by x square. You can see on the right hand side in that bracket, I've given the formulas. Differentiation of 1 by x square we know is minus 2 by x cube. That is how we get minus 2 divided by z plus I the whole cube. Now z is replaced with I to get our residue represented by equation number 1. Now using Cauchy residue theorem, we find that the value of the integral is pi by 2. That is by merely substituting r's value from equation 1, and whatever cancellations have to be done have been done. That's how you get equation 2. Now we will take equation 2 and substitute it on the left hand side of equation star so that we get equation 3. On this equation we apply the Cauchy's lemma. As r tends to infinity, integral over s ds by 1 plus z square the whole square tends to 0. That's how equation 3 can be rewritten as pi by 2 equal to minus infinity to infinity dx by 1 plus x square the whole square plus 0. The integral is written on the left hand side and the numerical value is written on the right hand side. Then we proceed further to use the definite minus infinity infinity dx by 1 plus x square the whole square can be rewritten as 2 times 0 to infinity dx by 1 plus x square the whole square. Substitute equation 4 on the left hand side, that is pi by 2. Then bring 2 from the right hand side to the left hand side to get the final answer. We have integral 0 to infinity dx divided by 1 plus x square the whole square equal to pi by 4, completing the problem. So with this we complete a few problems in type 1. Let us look at a few examples in type 2. Look at problem 1. The question here is evaluate integral minus infinity to infinity cos x divided by x square plus a square into x square plus b square dx using contour integration given a greater than b greater than 0. How do we recognize that the problem is a type 1 problem? The limit is minus infinity infinity. The numerator is p of x, that is 1. The denominator is x square plus a square into x square plus b square, that is q of x. And along with the p of x in the numerator we have cos x, indicating it is a type 2 problem. Whenever the integrand consists in the numerator either cos mx or sin mx, the problem is a type 2 problem. The contour is described exactly in the same manner as type 1 problems. Here the integrand consisted of cos x. Please look at the note given to you in the box on the right side of slide number 49. If the integrand has cos mx or sin mx, then we consider e power imz in the contour integral. Here integrand has cos x, that is m is equal to 1, hence we take e power iz in the contour integral, and that explains the reason for writing iz, e power iz in equation star throughout. Now we evaluate the left hand side integral by Cauchy residue theorem. The function here is e power iz by z square plus a square into z square plus b square. The singularities of this function are given by equating denominator to 0, and the denominator is already seen in a set of problems earlier. So the pole evaluation etc. remains the same. Two poles lie inside, two poles lie outside. For the two poles that are inside, we evaluate the residue using formula number 1. See that f of z is replaced with e power iz by z square plus a square into z square plus b square. Factorize z square plus a square, keep z square plus b square as it is, z minus ai gets cancelled, substitute z equal to ai to get equation number 1. A similar procedure is used for evaluating the second residue using formula number 1, and the final value of the residue is given in equation 2. The steps are self-explanatory. Substitute R1 and R2, that is equation 1 and equation 2, in the Cauchy residue theorem statement. Observe that in the last step of slide 31, 2i a square minus b square can be taken outside on the denominator. So what will remain inside will be minus e power minus a divided by a plus e power minus b divided by b, and that is what you will find in the next slide. Now 2 and I will get cancelled, and that's how you get equation number 3. We take equation 3 and substitute on the left hand side of equation star to get our equation 4. We don't use Cauchy's lemma. The problem is a problem of type 2 here. Therefore, we use Jordan's lemma. So as r tends to infinity, integral over s e power iz by z square plus a square z square plus b square dz tends to 0. That is the second integral on the right hand side of equation 4. That is how you get the next equation. We are replacing r with infinity, and the second integral is replaced with 0 to get the final result. See that what we are asked in the problem does not have e power ix but cos x. Now in the next slide, I have replaced e power ix with cos x plus I sin x by using Euler's formula. The integral on the left hand side is split into two parts. It has a real part and an imaginary part. We compare the real parts in this particular problem because the original question had a cos in it. If it was a sine, we would have compared the imaginary part. So comparing the real parts, we get the required result. Please remember that the real part on the left hand side is integral minus infinity infinity cos x by x square plus a square x square plus b square dx. And on the right hand side, the entire value is the real part because it does not have an I at all, and that is on comparison gives you the final answer. To understand the comparison of the imaginary part, we take up the second example, second problem. Evaluate integral 0 to infinity x sin x by x square plus a square dx using contour integration. We consider the contour exactly in the same manner as in the previous set of problems. We write equation star. Again, observe that the integrand here has sin x. If it is sin x, then we write e power iz on the contour integral. And that is why we find e power iz occurring in the equation star. Evaluate the left hand side of equation star using Cauchy residue theorem. The function is z e power iz by z square plus a square. The singularities are obtained by equating denominator to 0. That is z square plus a square equal to 0, which can be factorized as z minus ai into z plus ai equal to 0, meaning z equal to ai and minus ai are the poles. Both of them are order 1 poles. Of the two poles, ai lies inside and minus ai lies outside, so we evaluate only one residue using formula number 1. Observe the evaluation of the residue given there in steps. See that the final answer for the residue here is e power minus a divided by 2, which is represented by equation number 1. Use the Cauchy residue theorem. Integral over c f of z dz equal to 2 pi I into sum of residues. We have only one residue represented by r, and the value for it is replaced with equation number 1. So 2 and 2 get cancelled, and our final equation 2 is integral over c z e power iz by z square plus a square dz equals pi I e power minus a. Now this equation 2 is replaced in the left hand side of equation star to get our equation 3. Using Jordan's lemma, as r tends to infinity, integral over s z e power iz by z square plus a square dz tends to 0, and that's how you get the final result. Integral minus infinity infinity x e power ix by x square plus a square dx equal to pi I e power minus a. Now we rewrite e power ix as cos x plus I sin x, represented in the next slide. By replacing using Euler's formula cos x plus I sin x, we can write the integral on the left hand side in two parts, the real part and the imaginary part. Now we compare the imaginary part because our original problem had a sign in it. So by comparing the imaginary part, we get equation 4. Now again, minus infinity infinity of an even function can be written as 2 times 0 to infinity of that function, and therefore we get that particular result here. We replace equation 4, 2 is brought on to the left hand side, then we write the integral on the left and the numerical value on the right to get the final answer represented by the box in slide number 58. A similar example has been taken in the third problem. It is given as problem 2. It's actually problem 3. Please make a note of that change. The contour is described in the same manner. Now the integrand had cos mx, therefore we take e power imz, and finally we will be doing a comparison of the real part. The procedure is exactly the same. Please go through the various slides. You will be able to understand because all the steps are self-explanatory, and whatever formula is used, I have represented it on the right side of the point of application itself. We use Cauchy residue theorem to get equation 2, and then we use Jordan's lemma to get the required result. Now we rewrite e power imx as cos mx plus I sin mx, and then split the integral on the left hand side into two parts and make a comparison of the real part because the original problem had a cos mx. That is how you get equation number 4. But the question that was given to us had integral from 0 to infinity, but here what we have evaluated in 4 is minus infinity infinity. So use the properties of definite integral. Minus infinity infinity cos mx by x square plus a square dx equals 2 times 0 to infinity cos mx by x square plus a square dx. That is because of the reason that cos mx by x square plus a square is an even function of x. That is how we use that particular property, and by manipulating the terms, we get the required result as represented in the last box statement of our slide number 63, completing the problem. I am sure you are able to understand problems in type 1 and type 2, and how Cauchy residue theorem can be used as an effective tool in evaluating type 1, type 2 types of integrals.